Hi, today I'm going to talk about the particle in a box theory. Not theory, a model. Okay, particle in a box, or in a well, or in some other name. Okay, so what is particle in a box? It's a particle in a box is a model which represents that show the difference between the quantum mechanics and Newton mechanics. Okay, suppose in a room. I have a room. Oops. Okay, I have a room. Oh, okay. I put some ball, a big ball inside. Okay, and then I close the room. I don't know where the ball is. Okay, I close the door, and I say that the probability to find the ball here is equal to here, right? Because we don't know where the ball is, or here. They have all the same possibility to find a ball, right? This is real in Newton mechanics, but this does not exist in a quantum mechanics, or in a very small scale, in a nanometer scale. Like this is a okay. Oh wait. Okay. This is the x and y axis. Okay. And this is my room. Inside here is my room. This is my room. Okay. Now I create a wall, which this is the wall. Okay, particle cannot go through this wall because in Newton mechanics, first the ball cannot go through the wall, right? Because the wall, they cannot penetrate through the wall because they don't have like enough momentum to break the wall. In this case, in quantum mechanics case, they can the particle cannot go through the wall because this has a potential energy px, okay, of infinity, so they cannot penetrate here, and this have a potential energy of 0. Okay, here, so there is no energy or no anything acting on it. Okay, so they just roam around here, go around here. Okay. So now you know the concept that they're gonna explain how we're gonna see the particle, like in here or here, they do not have the same probability. Here or here, they do not have the same probability that we will find the particle, which can be described by the wave function. Okay, so let's start. Now I say that this particle is a free particle, which means they roam around here wherever they want. Okay, which they follow this equation, psi of x. This is time independent. I'm gonna go with time independent way. Okay, equal to a some constant, psi k another constant, x plus another constant, b cosine, and k the same constant as this, and x. Okay, now I said I would like to differentiate it. Okay, psi x, I want to differentiate by okay, by dx. So what you got here, this thing come out, right? A k, and this thing different sign, you differentiate sign, you got cosine, and kx. And now b, right? And you got this k, and cosine, you differentiate, it's minus sign, so I push minus in front of here. Okay, sine and kx. Oops. Okay, now I differentiate again. Okay, equal to what? You got the same a, you get another k, so k square. Cosine, you differentiate, you got a minus sign. Okay, minus sine kx, and sine you differentiate, you got oh wait, cosine, yeah, correct, minus b of course, and k squared, and sine you differentiate, you got cosine. Okay, now you got 3 of this. Okay, we will use 2 of it. Okay, now I will write my Schrodinger equation, which is minus I'll write the short form first. H Hamiltonian operator on psi function equal to energy of psi function, and now the full form over 2 is h bar squared over 2m, and gradient operator squared plus the potential energy, okay, on a psi function equal to energy on psi function. Now what is the gradient operator here? Gradient operator is, for in this case they just differentiate this thing by 2 times. Okay, so if, like I say, this is my function, right? Psi x my function, I gradient, gradient is a upside down triangle, gradient my psi function, you will get the differentiate psi by dx. Okay, in this case, okay, of course psi square is this differentiated by 2 times. Okay, no, not x, psi. Okay, now so minus h bar square over 2m, and differentiate by psi function by 2 times, plus some potential energy of my psi function equal to the E energy of my psi function on my psi function. Okay, now you get this, and you see this and this and this, right? And your psi function is up here. See, they are the same, and this one, for this one you just use this one, right? Okay, how about the potential energy? Potential energy, I said that particle roaming here, you got what? The potential energy is 0, so this term is 0. Okay, so now you get only minus h bar square over 2m, and for easier just write like this, okay, equal to E and this thing. Okay, now let's substitute everything in. Okay, so minus h bar square over 2m, and then multiply on my function is let's use this one, just copy them. Okay, now equal to E, and my original function, which is a a sine kx plus b cosine kx. Okay, now I want to move this thing around here. Okay, I move this part to hit this part. Okay, so minus a k square sine kx, my highlighting is shit, kx minus b k square cosine kx equal to 2me, okay, 2me over h bar square, and of course a minus in front. Okay, and multiply on this. I'll just multiply it in. Okay, now E, okay, and I push the minus in front and a in here. Okay, then sine kx plus b 2me over h bar square, and this must be minus. Okay, I multiply this coefficient in. Okay, and cosine kx. Oh, no, yes. Okay. Now on the both sides of this equation must be equal, right? So you see something, right? A here, A, right? Sine here, cosine here, B here. Oh, great. Now you get this, and of course the minus in front, this and minus in front, this and minus in front, this and minus in front. Okay. Oh yeah. Now you see that minus k square, which they are completely equal to the minus 2me over h bar square, right? I take the minus out. K square is 2me over h bar square. K is now equal to square root of 2me over h bar square. Okay. Now, at first my function was a lot of unknown constant, right? Now we know some constant. Now I will substitute it in. Now my function is now it's the function of psi of x, which is time independent. A sine and k square root of 2me over h bar square. Okay, and then what, x, okay, and x, okay, plus b, which is another constant, cosine square root of 2me over h bar square, and then x, right? Now this is my current, we know here. Okay, this is my current equation. Now I forgot to tell you one thing, that in this well, okay, in this box, wait, I'll write down here. In this box, okay, the chance to see the prime particle here and here, which is the 0 and point name A, is 0. So you will not find here or here. So the wave function will be like, it's like this or like this, right? Which is 0 and A, right? 0 and A here. So you will not see my particle here and here. And of course my psi function of 0 at this point must be 0, and this point psi function at A point is also 0. Okay, now you got two equations, two more things to find your A and B. Okay, psi of x, okay, and now no, I just substituted in. Okay, psi of 0, which equal to 0, equal to A sine square root 2me over h bar square, and x is 0, plus b cosine square root of 2me over h bar square, and x is 0. Okay, now 0 multiplied by this, you got a 0, right? And cosine 0 is 1, right? So in order to you to get a 0, the b constant must be 0, or otherwise it will not be 0, correct? So my b constant is 0. Okay, so this term cancel out. Okay, now you get that psi 0, which equal to 0, equal to A sine square root 2me over h bar square, and 0 here. Okay, this multiplies 0, so the term inside is 0. Okay, sine 0 is 0, right? So A can be may be not a 0, not a 0. Okay, but B must be 0. So A may be some other things that are not 0. But okay, now my next thing is psi of A is also equal to 0, right? So A psi square root of 2m e over h bar, and a, right, I replace the x, a is 0. Okay, in order to get a 0, right, let's see that so a maybe not a 0, so this thing must be 0, right? So in order for the sign to be 0, okay, it is something, right? In order for sign to be 0, right, the sign will be, sign of x will be 0 at x is equal to what? 0, right? Pi, or like 90 degree, right? Or 2 pi, or oh, not 90, or 180 degree, or 360 degree, right? And 3 pi. So it's obviously n pi, right? Okay, so I get that this inside must be n pi in order it to be 0. So I delete this one. So square root of 2m e over h bar square, and a equal to what? Equal to this, right? So in order for it to be 0, for the phi function to be 0, so it will be n pi. Okay, I move a down here. Square root of 2m e over h bar square equal to n pi over a, right? Now we move on to our equation. At first, our equation is psi of x equal to a psi square root 2m e over h bar square, right? And x. Now we say that this thing equal to this thing. We change, okay? So a psi n pi over a and multiply by x is now my wave function now, okay? Now we change to the second time. We move on, okay? At first we got this. Now we got this, okay? Which they are the same, okay? We just add more condition and find some more constant inside, or variable inside. Now what constant now we have to find? A, right? That's one more thing to find, a. Now how do we find a? Now you talk about the normalization. Now normalization is to find some constant, to find some number and put inside our equation, okay? Like we find some find some number, just any number, okay? Find some number to put inside our equation in order to get this integral from some place to some place of psi and psi star dv. If this is a three-dimensional, dv, v is the volume, okay? But this is a one-dimensional, so dx, okay, is equal to 1. Well, what is this? This represents a possibility that we will find our particle in between this area, okay? So we in our case is a box, right, from 0 to a. So integral of 0 to a of psi and psi star dx equal to 1. So we must find the particle in here because they must be in here. They cannot go out, okay? Now, so the possibility of finding it here is 1. So that we must find that in here. Like I say that we must find some food in the cafeteria, or we must find some water in the bathroom, or something like that, okay? Now psi and, well, what is psi star? Psi normally is if psi is a complex number function, okay? Like I say psi is 3 plus 4i, which I is a complex part, imaginary part, right? This is imaginary part, this is real part. The conjugate of this thing is 3 minus 4i, okay? And we call this a psi star, okay? This is like some examples. So or this thing called the complex conjugate, okay? Complex conjugate. But let's see our function. You see any I in here? You see any complex number in here? No. So in our case, psi is equal to psi star. Like I said, my function is function is 3. My psi with conjugate complex conjugate equal to what? 3. The same, because there are no imaginary part. Okay. Now in our case, psi is equal to psi star. So I just write it again, 0 to a, right? Of psi, I write absolute square dx, okay, equal to 1. Okay, now integral of from 0 to a of a sine, okay, a square, right? Sine square n pi over a and then x, okay, dx equal to 1. Okay, now I pull a out. It's a constant a, so a square integral of from 0 to a of psi and n pi over a and x and dx equal to 1. Now this is mathematics. Oops, wait, my square gone. Okay, this thing, right? If from the trigonometry, cosine of 2a is equal to what? Is equal to 1 minus 1 minus 2 sine square 2a, not 2a, of a. Okay, now I move this thing back. Okay, cosine 2a minus 1 and equal to minus 2 sine a, right? I move minus 2 down here, equal to sine square a. Okay, but I don't want the minus in front, right? Equal to 1 minus cosine 2a over 2. Okay, now we use this thing, put it back in. Okay, what do we got now? A square integral from 0 to a of 1 minus cosine of 2n pi over a and x, okay, right, divided by 2 and dx equal to 1. Okay, I pull the 1 over 2, okay, I pull the 1 over 2 out, so we got a square over 2 integrate from 0 to a 1 minus cosine of 2n pi over a x dx, okay, equal to 1. Now we split the integrate to integral from 0 to a of 1 dx, right, and minus a square over 2 again, because we multiply it in like this, and integral from 0 to a of cosine 2n pi over a and x dx, okay, equal to 1. Now this thing, of course, you get a square over 2 and a, right, minus okay, you integrate the I'm using the substitution technique. This is a u, right? Okay, I will not integrate, and I will not show you the integral, just give you the answer. Okay, a square over 2 and a over 2 n pi, right? Then sine 2n pi over a x, okay, and then you need to substitute from 0 from a minus 0, and this thing equal to 1. Okay, now this part we don't need to worry about it. Okay, we worry about this part. We substitute a, okay, from a, if we put this a inside and a decrease 2n pi, of course, you get 2n pi. Okay, sine of 2n pi is of course 0. So this thing for a, you get the whole part is 0. And now you try to substitute 0 inside here. 0 of course sine 0, and then everything inside also 0. So this also 0. So it will be 2 over 2a minus 0 minus 0, right? Okay, like this, right? But this don't have any meaning, equal to 1. So what you see here, equal to 1. What you see here, you get an a now. You move 2 up and a down and put a square root n equal to square root of 2 over a. Right? Now you get the a. Okay? Your equation is now complete. Your sine function now x is equal to 1. Let's see from the top. Here. A sine this to here, right? A sine n pi over a and x, right? Now we know the a. We put the a in. Oops. Square root of 2 over a of sine n pi over a x, right? Now this is the final equation we got, because we have everything we want to know now. Okay? Now, do we forget something? Did you forget something? Let's go to the top. How about E here? Do we forget about the E? Right? We want to know the energy. Okay? E from where is it? From okay, yeah, this part. Okay? Yeah. Square root of 2me over h bar square equal to n pi over a, right? I copy down here. So finding the energy. Oh no, not finding, find the E. Okay? So now square root of I'll use the thicker pen. Square root of 2me over h bar square equal to n pi over a, right? Okay. Now I square by on both sides. You get 2m e. My m is shit. 2m e over h bar square equal to n square pi square over a square, right? I wanted only the e. I move this thing up, move both this down. You get e equal to n square pi square. Yeah, and h bar square over 2m, right? Now h bar, as you know that h bar is h over 2 pi, right? So you get the square, right? And this will be 4. So you replace it here, substitute it here. It's n square pi square h square over 4 multiplied by 2 is 8, and pi square m. This thing decrease, you get an n square h square and 8m. And wait, what? Oh, not m, a. 2m. Wait, m. Oh, I missed a. Yeah. Okay. Now, E is equal to n square h square over 8m a square. Now, this is the energy that I get, and this is the wave function. Okay, now this is the theory, the model of the particle in a box. And like from this function, okay, I just show you a little more. This is my okay, this is an energy, okay, and this is the x distance, and this is the point A, okay, and this is the wall, this is the wall, okay, this is 0. Now if the n quantum number equal to 1, you get a function like this, and n, you get an n equal to 2, you get a function like this. Now you get a 3, you get it like this. Okay, n equal 3, n equal 2, and n equal 1. Okay, now if you I just like some, okay, my drawing is not so good, and this is how particle behave. But how will you like the possibility, okay, possibility to find for the n equal to 1? Of course you get the same thing, and don't forget that the possibility is this one. Okay, and for in this case you just get this one, a size square. Okay, absolute size square. And in for the n equal to, you get two bump like this. Okay, and in for the n equal to 3, you get 3 bump like this, right? N equal to 3, n equal to 2, n equal to 1. Okay, so this is the probability to find your particle in the position in your box. Okay, so this you will not find for the box. It's called the node. Okay, you will not find here, and this is the highest possibility you will find. Okay, so this is all about the particle in the box now. Thank you for watching.